All right, so the second part of section 4.1, we begin with this question, which is an example found in the OpenStax textbook. It's called example 4.3. It's about a rocket launch. And so the question goes pretty much as follows. It's a little paraphrased. A rocket is vertically launched, goes straight up from a spot 5,000 feet away from you with an initial velocity of 600 feet per second. How fast is your angle of elevation as you look up to the rocket changing when the rocket is 1,000 feet above the ground? Okay, so what do you want to do first? I hope, okay, I certainly hope that the first thing you would want to do is to draw a picture. Okay, so you can do a little stick figure for yourself. Unless you are a good artist, you can draw this better. Draw a rocket. I don't know what the rocket looks like. You know, maybe it looks like this. Yeah. All right. Anyway, it's going up like this, straight up in the air. It's launched at what, 5,000 feet away from you, right? All right. And then the question is, okay, so let's say if the rocket's right here, then your angle, you'll be looking in this way, and this is the visual angle, the angle of elevation. That would be that angle. So the angle from the horizontal plane as you look up to where the rocket is. Okay, that's the angle of elevation, and that is of course changing. And the question is, let's try to find out how fast theta is changing when the this distance. Let's call this height h. H is increasing. Well, it's increasing at 600 feet per second. But when h is 1,000, let's try to find how fast theta is changing. Okay, so you can call this first step, you know, drawing the picture, and then of course the next step you want to identify what you know, and you also want to give the names for these quantities changing with respect to time, right? So like I have already wrote down h, so let's say h is the height, and this is in feet of the rocket. You can also call this the position of the rocket. H of 0 is, of course, 0, right? And theta is this angle of elevation, angle at which you're looking up, right? And we are trying to find what? The theta dt, right? Because you are trying to, I mean, the question says, how fast is the angle changing, right? Do we know dh dt? That is the rate at which h is changing, otherwise known as the vertical velocity of the rocket, and that's 600 feet, okay, feet per second. Actually, the problem says that it's not just the initial velocity, but the plane, I mean, the rocket is going up at the constant velocity. It is important, okay? We do not need to know that it is moving constantly at 600 feet per second, right? So that is something we already are given. And so anything else do we need to know? I think this is it. I mean, we have 5,000 feet written in here, right? So how are h theta and 5,000 related to each other? Okay, so this is well, simple trigonometry. This time we actually have to use trigonometry because we are given h and 5,000, and you can see h over 5,000 is the opposite over adjacent, and that is called the tangent of theta. Okay, right? Can we differentiate? And by the way, this h is changing, t is changing with respect to time. So when you differentiate this, you get, actually, can I write this the other way around? The tangent of theta is equal to this. Tangent of theta, which is changing with time, is this, right? All right, let's try to differentiate both sides. You have secant square theta multiplied by, of course, the derivative of theta with respect to time, that's the implicit differentiation part, is equal to, now 1 over 5,000 is just a constant multiple. Okay, so 5,000 will remain in the denominator. The top just becomes the h dt, okay, which we already know, by the way. That's 600 feet per second over 5,000. Okay, at this point, you can simplify this if you like. Okay, that's just a 6 over 50. You could actually write this as 3 over 25. No, why not simplify this, right? So d theta dt turns out to be Now let's multiply both sides, well, divide both sides by secant square, which is equivalent to multiplying both sides of the equation by cosine square. So you get cosine square times 3/25. Why don't we just write as 3 cosine square theta all over 25. And that's really the answer, right? Okay, now, I mean, that's the answer for d theta dt. And you can get that as soon as you know what cosine of theta is. What is cosine of theta? When, let's see, when the rocket is 1,000 feet above the ground. Notice here, I didn't use this because this is one of those things constantly changing, and I can't plug this number in until we have done the differentiation, right? The rocket is 1,000. So when you want to find this, when h is 1,000. Okay. So when h is 1,000, you have this picture, which is 5,000 and 1,000. Okay. So what is theta? Actually, what you're looking for is not just theta, but cosine of theta, right? So why don't we find the cosine of theta? Well, that's the question, okay? But that's not too hard to find because the hypotenuse is going to be, this will be, we need a name for this one here, right? It's x. Let's say x. I don't want to say the hypotenuse h because we already used h for something else, the height. So x is going to be 1,000 square plus 5,000 square and the square root of that, right? So cosine of theta is going to be 5,000 over this whole thing. Okay, unfortunately, it's a large number, but you know, we can handle large numbers like millions, right? So, okay, we have this expression. So d theta dt is, let's say, 3/25. Okay, and now I'm going to multiply this by cosine square. Now, cosine unfortunately had a square root sign, but cosine square is not going to have the square root sign, which is fortunate. Okay, nice. We don't have to worry about that theta. So the answer is going to be 1,000. The denominator is going to be 1,000 squared plus 5,000 square. The top is going to be 5,000 square, right? Now, again, these are large numbers, but we can handle this, right? The top is 5 squared times 1,000 times 1,000. That's 25 million. Okay. Wow, right? Now, the bottom is 1 million times 25 million plus 25 million. So it's going to be 26 million, right? And then the millions cancel. So that's kind of nice. And in fact, 25 also cancel. Right? Now you can depend on your calculator to do these, but you know, be careful when you enter large numbers in here. I didn't have to use a calculator because you can do this by hand, right? So the answer turns out to be 3/26. Wow, that's simple. All right, 3/26. What? Okay, that, by the way, if you now take a calculator and calculate this number, it turns out to be 0.1154 approximately. Again, I don't really care how many decimal places you find a number to, but I think this is pretty reasonable. 0.1154 watt. Okay, now remember, we are measuring the angle theta. And as you use calculus, remember, can we just use degrees here? And the answer is absolutely not. Okay. Now why? Well, because we use the fact that, you know, the derivative of tangent is secant, right? A secant square. The derivative of sine is cosine, and so on. And in all throughout the derivation in chapter 3 of these differentiation formulas, we assumed, okay, we used things like the limit of this is equal to 1 as x approaches 0. That whole thing is based on the fact that we are using radians, okay? So we have no choice but to use radians. So just remember, in calculus, anytime you have angles, using calculus, you're going to have to use radians. All right, so this is radians. And of course, this is speed with the rate of change. So it's radians with respect to the time second. So you can say that the angle of elevation, your visual angle as you look up to the moving rocket, is changing at 0.1154 radians per second. Not very satisfying, huh? You could change it. You could multiply this by 360 and divide it by 2 pi, or multiply this by 180 and divide by pi to get, this is actually 6.61 degrees, approximately 6.61 degrees per second. And, you know, even the engineers, even the rocket scientists use degrees when they are looking at, you know, angle of elevation. So it is appropriate to actually write this as an answer, even though this is a completely fine answer for this calculus question, because again, in calculus, we use radians. But if you're looking for a practical meaning of it, you could say, so you can communicate to the general audience in public that the angle is increasing at 6.61 degrees per second. All right. If you go back and look at this, what's going to happen as this increases, you know, as what height used to be 1,000, but it gets bigger and bigger. And as you do so, the cosine gets bigger and bigger, right? So, well, does it? This gets bigger and bigger. So actually the theta gets bigger and bigger, approaching 90. So the cosine actually starts to get smaller and smaller and get closer to 0, right? Because cosine is the 5,000 over the hypotenuse, and the hypotenuse increases. Yeah, so this actually gets smaller and smaller. And that makes sense because the angle is going to change, but you know, toward the end, when the rocket's really, really high, the angle is close to 90 degrees, and it's not going to change very much after a while. So the rate of change, again, theta is increasing, but the rate of the change of theta is going to get smaller and smaller. And so that this equation does make sense from that respect. All right, I have one more problem prepared. So let me draw a picture, and then I'll ask you this question about the funnel. And this is example 4.4 in the book. All right, so this is, again, a very typical calculus problem about water being drained from a pool or from a container or something, okay? Like I said, every calculus problem has one of these questions at least. All right, so the funnel, and you can tell what's happening is, you know, the funnel, the water is going down here, and let's read the question first. Water is being drained with a funnel at 0.03, this is cubic feet per second. Okay, the radius of the funnel is 1 foot in. Okay, so this is radius, so the diameter is 2 feet, and then the height is 2 feet. Now, why is this important? Okay, well, it is important because this 1 to 2 ratio, radius to height is 1 to 2, is going to be the same for the remaining part of this water. The radius at any point is going to be r, that's half of the height of the water level of the level of the water, the height of the water inside at any point. Okay, how fast is the water height h changing? That's the height changing when h is 1/2 of a foot or 6 inches, right? It's going down, 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 and you can imagine that the height is changing what, maybe quicker and quicker as you start to drain more and more. Yeah, I think that's what's happening, because as the entire volume gets smaller, even if you're draining at the same speed, the h is going to be changing faster and faster. I think you can picture that, right? All right, so now there are lots of things to observe at this point, right? But the problem is the way, at least the way I state it, gives you h, right? H is the height, and r is the radius of the remaining water as a cone. See, anytime the water is remaining and is still being drained, it's going to be like the cone. So we have the radius and the height, right? So height divided by the radius is always going to be 2/1, which is 2, okay? Always. And that's something to remember. okay? Because or you could say that H is equal to, let's say, maybe I can say R. Did I say that? H is equal to 2R. Or you can say R is always going to be half of the height. We are going to use one of these, okay? Because right now we have several things changing, okay? What do we mean by that? Well, let's go ahead and try to remember what the equation is. If V, see, this is the change in volume, right? So let V be the volume of the water in this funnel. So then V of T, okay, how is that related to H and R? Do you know the equation of the cone, the volume of the cone with the height H and radius R? Okay, you may or may not know this, I hope you do. It is 1/3 times the volume of the corresponding circular cylinder, which is pi r squared H. Okay, pi r squared, oh, maybe here. Let me just go ahead and skip the V, the time T. The volume is 1/3 times pi r squared H. Okay, so this part represents, of course, the volume of a circular, not the cone, circular cylinder, but the cone has exactly 1/3 of the volume. Who found this? Okay, it turns out Archimedes knew this 1/3, this equation, about 25 centuries ago, not very recently. All right, but what is changing here? V is changing, R is changing, H is changing. Okay, so here, if you include the reference, the independent variable T, volume at any time T is 1/3 pi R of T squared, then HT. All right, this is the first time I have two different functions giving you a third function, right? We've only had two things. So we're going to have to do something because we can't take the, we can't take the derivative when you have three functions. That's not going to help you find the answer very easily, just in calculus 1. In more advanced calculus, you may have two variables. All right, so here, this tells you how H and R are related to each other, right? So you can switch one of these. What I'm going to do is to write R as H over 2, all right? Since R of T is always 1/2 of H, we can rewrite V as 1/3 pi. Oh, so R square is going to be written as H square over 4, and then you have another H of T, right? And I do this so that you only have two functions that are changing. See, when you do related rates, you want to compare two rates and not three, okay? Because that will make things much harder. All right, so what do we have here? This is 1/12 because you have 3 times 4, and then pi on the top, and then you have H of T to the 3rd power, right? So that's actually not too difficult, right? We have H changing, and of course we know R is changing, as well, but we have really the V as a function of height. And so that is manageable. All right, now we differentiate. dV dt is equal to pi over 12, and then you have 3 H of T squared times dH dt. Get that? Okay, again, learn to differentiate with respect to time. All you have to do is to think of this as an inside function using the chain rule or implicit differentiation. It's 3 times H squared times the derivative of the inside function. We are looking for this, okay? What does the question say? When the height is 1/2, okay? So we know at the particular point in question, we know this is 1/2, right? All right, so, oh, by the way, let's simplify this also. 3 and 12. So this is pi over 4 H of T square dH dt. Okay. dV dt is a given, isn't it? It's 0.03. What are we looking for? dH dt. Okay, let's just go ahead and solve for that. Okay, so I'm going to divide both sides by that. All right, so dv dt is on one side, and then you have pi over 4 times h squared on the other side. Now we know dv dt to be what? 0.03. All right, now let's be careful here. Right? Because we know positive and negative numbers, the volume is actually not increasing, right? If I put 0.03, that would indicate that the volume is increasing. But because the water is draining, let's just write this as negative 0.03 cubic feet per second, right? And then you divide this by pi over 4. Well, 4 is a denominator. Let's just multiply this by 4 on the top. The pi stays in the bottom. And h squared, h is squared. So this will just becomes negative 0.12 divided by pi times h squared. Now this, maybe not. This is too wordy in the sense. Okay, because like why move this 4 up in the top? You don't have to do it that way. You can just simply plug in at this point. H is equal to 1/2. So at h is equal to 1/2 foot, which is 0.5. I think we can easily find dH dt to be negative 0.12 all over pi times 0.5 squared. All right, so this will be negative 0.02 over 0.25 pi. If you don't like the fraction part, that's okay too. It's basically negative 12 over 25 pi. All right, take your calculator out. Okay, make sure you put pi in the denominator, not on the numerator, and you will find that the answer is negative 0.153. Okay, that's the easy part. Okay, let's figure out the units. For the units, remember the volume is measured in terms of cubic feet, right? And of course, with respect to time, which is second. So this is feet. Remember, h is a one-dimensional thing. It's length. So it's feet per second. So it is decreasing at 0.153 feet per second, or foot by second. If you multiply this by 12, you can get this in inches per second. And so that will give you the answer. Okay, so I have worked on 4 problems. The first 2 are similar. The third and the fourth were quite different, but you have all the ingredients, all the skills necessary to solve a wide variety of related rates problems. Remember the guidelines. The general guidelines is write down what you know, right? Okay, and then start with an equation, whether it's based on geometry or trigonometry or your drawing, okay? Or maybe the equation will be given to you at the beginning. And you differentiate with respect to time, and then you plug in that given information, not anytime sooner, right? And then, of course, you can solve for the unknown rate. All right, so now it's your time to try your mastery of this subject. So go ahead and do your assignment and learn related rates well.